Start, I'd just like to thank our sponsors. There's a number of sponsors, you'll find them listed on our web pages, who have given their time, their energy, their people. They'll be sharing their knowledge and experiences with us. So really a big thank you to all the people, all those sponsors who are contributing to this conference and making it possible and making it interesting. Now I'm going to hand over to Madeline, I hope she's ready, to take over the presentation. Madeline Cheah, who's the cybersecurity lead at HORIBA MIRA. Hopefully I've said HORIBA MIRA correctly, because it's not how I'd expect to be pronounced in English. And she's going to tell us something about cybersecurity and future mobility.
Hi, everyone. Thank you for attending my talk, and thank you also to Tesena for inviting me to speak here. It's been really good getting this talk ready, and I hope to share some interesting pointers with you. So let me share my slide. Hopefully everyone can see that. Phil, can you see that?
Yeah, I can see that.
Fantastic. So today we're going to explore a little bit about automotive cybersecurity and future mobility, you know, this whole new world of self-driving cars and the sort of implications that there are on security testing of these cars. And they, you know, there are quite a few differences depending on the sector that you're in. So first of all, quickly just introducing HORIBA MIRA. So we're a global leader in engineering research and product testing. That includes vehicle engineering consultancy, test engineering services, and the third stream of revenue we have is the MIRA Technology part, which houses the MIRA Technology Institute, as well as a whole bunch of tenants who like to use our proving ground. Me, myself, as the cybersecurity innovation lead at HORIBA MIRA, I have 8+ years experience in cybersecurity in a range of sectors, including, oh, that's glitched, including transportation, computing, IoT, and in education as well. So yeah, welcome to my talk. So the first thing I wanted to talk about was this concept of cybersecurity. And really, this is my absolute favorite picture of cybersecurity. I don't know where it is, but if we have a look, this is the product with its intended functionality, whether that's a car or an IoT device. And as you can see, the product does what it says on the tin. It is exactly acting as intended. However, a lot of the times criminals find ways around it, or they find ways through it, or they find flaws with it. And these represent, you know, the skid marks that I represent the security exploits, which are visible to us. In the entire sort of future mobility and automotive space, however, there's still all of that that could be used even if we start protecting the boundaries ever outwards. And this, in a nutshell, is basically the practice of cybersecurity everywhere, not just in automotive, but very much a focus in automotive. So one of the things I wanted to talk about first is what do we know? You know, what kind of areas do we have some idea, some information, some data coming through in terms of cybersecurity practice? And one of the things we know in future mobility in connected autonomous vehicles and in cars is that we have some key enablers. And one of those key enablers is artificial intelligence. Lots and lots of examples of adversarial testing on artificial intelligence, adversarial security testing, you know, on computer vision, where they show that if you replace a pixel with something else, then it recognizes a turtle instead of a stop sign or something. But, you know, it's not just artificial intelligence on board. We have artificial intelligence possibly connected to an off-board algorithm or model, or sending data up as well. And here we actually know, although this is a key enabler, we don't quite know what the interactions between these different AIs would be, different agents. And that in itself poses a bit of a challenge, because of course interagent interaction usually can lead to emergent behavior. We've got loads of sensor technologies that are taking place. So, you know, we've got ultrasound and radar and LiDAR and so forth, and all of those would need testing as well. Not just the hardware part of it, but also its operation, and also, of course, its security, because these are the vehicle's eyes and ears. And if things that are entering these sensors are wrong, or if the sensor itself is interpreting or recording them wrong, then we have a problem. Connectivity, absolutely key. Can't have a connected autonomous vehicle without connectivity, and there's a whole area of testing there as well. And then underlying it all is data. So this data is really important, and it's the basis for everything that we can see in a CAV. And on top of that, all this testing, especially security testing, which has safety implications, really enables trust. Trust from consumers, trust from users, trust from operators, and trust from the people designing them as well. So in the automotive world, there are a few limits and there are a few constraints that really kind of has a big implication on how security is deployed and how it's tested. And one of them is constrained systems. So in an automotive system and future autonomous vehicle systems, although the collective power of the distributed systems in the cars can be very large and can be enhanced by connection to the cloud, really there is a limit on the kind of the computational power available on each individual unit. And this constrained system means that we have to be really careful about protection like encryption, for example, since encryption can be computationally expensive, which means you slow down the signals that you want to protect. And unfortunately, in a car, the signals that you most want to protect are usually the most time-sensitive ones, like brake signals. We've got long life cycles, so this obviously impacts on testing and development as well. So we're not just talking the long life cycle of the vehicle's design, but we're also talking long life cycles on how long we expect them out to be in the road. And once we start talking about the ecosystem, which I'll go into later, that this long life cycles problem becomes even more. So the average time it takes to design a vehicle right through to production and having the vehicle on the road is around 7 years. The vehicle tends to be on the road between 12 and 15 years on average. So from design to the end of its lifetime, when it goes to the scrapyard or wherever, we're talking 20 odd years. Now in the software world, in the security world as well, that's a really long time. Supply chain and dealerships. So I mentioned connectivity there. We've got sort of supply chain security and how you test that and how you verify and validate that. But upstream, we've got the dealerships as well. How do they continuously monitor? I mean, continuous monitoring usually means testing iterations, but are dealerships, are they equipped to deal with that yet? And of course, as business models change when we go into the connected autonomous vehicle world, these business models will affect how things are tested as well, and how quickly they're tested maybe, and how often they're tested. Updates. So, in the IT world, for example, updates are usually, or patches are usually sort of managed and tested in a sandbox before deployment into the wider network. Now, for vehicles, this could be very different or very difficult because, of course, we're talking a huge volume of updates. We're depending possibly on wireless updates, which means we would need to depend on the quality of the signal, whether it's cellular or short range like Wi-Fi. We don't, at the moment, there are lots of issues with, how would you test for if an update decides to stop halfway because of a lack of connectivity, or an update with a car that hasn't been updated for a whole year, for example. You'll end up with hundreds of variations and how do we know this update won't cause a safety issue in one of these hundreds of variations? And we also have the ecosystem to consider. Now, obviously, with testing and with security testing especially, depending on what kind of testing you use, you might want to consider the scope of testing to be increased. So, for example, in terms of the ecosystem, do we just test the car, or do we test the car that's connected to the charging station? Do we test the phone that's connected to the car? Do we test the wearables that are connected to the car, seeing as they're all inputs to the car? Or the car could also be used as a vector, security-wise, to harm the charging station or the grid or whatever it is. So in terms of the system boundary, where do we stand? So, and the last bit around security testing is legislation. So in terms of the automotive industry, as I'll talk about later, security assurance is very much a part of the standards and legislation that are coming through. And security assurance one of the key enablers of that is to do a lot of testing. So, legislation is coming to drive this along. So that's sort of the stuff that we do know, some of the constraints and so forth. But what is it that we still need to understand in order to really grasp some of the implications on testing and security testing? So here I wanted to introduce this idea of Internet of Vehicles being a superset of the Internet of Things. But actually, it's actually a subset of Internet of Everything. And this is where we want to discuss some of the other pillars that may affect development and testing processes. So the first thing is things, and we'll go through that later, but also data, process, and people. So I'll be outlining some of the issues and some of the challenges that we face in these 4 pillars. So with regards to things, and also testing of these things, there are so many things on a car. So demonstrated attacks have already been proven on the CAN bus, for example. So the CAN bus on a car, the controller area network protocol on a car, is a protocol created for robustness. However, it is a legacy protocol. So it was last codified in 1993, and it's in every car today, possibly in every car in the near foreseeable future. It's in motorcycles and ships and so forth. So very much a ubiquitous thing. But because it's a legacy protocol, there's no space for security anymore. The OBD2 port is another thing that has opened up the car. So the onboard diagnostics port was meant to be a port that allowed for diagnostics of the car, but it also allows for attacks through it. And testing this would be really important as well, of course. Some of the demonstrated attacks, like car thefts, use this port to program new keys in order to steal the car. The immobilizer, so this is again a very old attack. The immobilizer can be swapped out or overridden. You can buy stuff for this on the internet for like £40, which is about 38 euros or something like that. Very cheap. And again, in terms of a demonstrated attack, used to steal cars. Keys are another target. So they're clone keys and creation of new keys or jamming of the keys as well to prevent the door being locked. So far, I mean, in terms of what's been demonstrated, is all for car theft. But of course, as we know, cars are becoming more and more intelligent. They're becoming more and more connected, and it's not inconceivable to expect that there are lots of players and criminals around the world who'd want to take advantage of that, and I'll speak about that a bit later. So now we go into demonstrated attacks in research. So the CD player, for example, and going back to my intended functionality kind of piece earlier, this researcher showed that if you took a CD, put some arbitrary code on it, and encoded it as music and put it into a certain kind of CD player, the CD player will play the music and therefore execute, and also then executed whatever was on there, which allowed them to reflash and pivot into control of the car. So you can see sometimes it pays to think about the wider system boundary, for example. Got lots of demonstrated attacks on Wi-Fi, lots of one really high-profile demonstrated attack on a car with a cellular network. And of course, interestingly, in terms of the cellular network, from April 2018, every car has to have what's called eCall, which is like an emergency call, which of course means it needs cellular connection. We've got sensors again to think of, so lots and lots of demonstrated attacks on cameras, ultrasound so far, and radar and LiDAR and GPS. So look at all these things. The car is already so complex. But there's actually more things coming, and this is where it has real implications for testing. We have predictive management systems, for example, so things like battery management systems that predict when you would need more power, less power, or try and predict what the best journey might be for you. And in terms of vehicles, or any vehicle, whether it's the vehicles of today or CAVs, connected autonomous vehicles of tomorrow, batteries are one of the most safety critical things. Either, we definitely don't want thermal runaway because that leads to fire and all sorts of very safety critical things. Telemedicine, so this is related to in-cabin occupant monitoring, but we've got privacy then to think about there as well, and whether we can test for security in terms of protecting people's personal data. This is being discussed right now in terms of emergency vehicles, or even your own vehicle that looks at driver well-being. Wireless charging, so and this is more around the ecosystem as well, in terms of the whole electrification drive. We've got peripheral devices that are being connected to the car, so smartphones are being used as keys and controls. There are now cars out there, and not even cabs, but cars out there where you can use use your mobile phone to get your car to self-park. We've got personal assistants coming along, and this is where it's really important as well, because to build trust, because in terms of personal assistants, they're obviously the front line to a consumer and to a user. And by messing about, making a personal assistant sound creepy, for example, it could really affect the trust that people have in this product. Telematics, as I mentioned earlier, we've got offboard computation happening, so lots of things being sent to the cloud to train up intelligent models and so forth. You've got in-cabin monitoring, and you've got external monitoring, so even more sensors being put onto the car. We've got different networking protocols coming along. So I mentioned CAN earlier as a legacy protocol. So now we've got different sort of Ethernet, automotive Ethernet, they call it, along with all the possible problems that come with Ethernet that we know about from the IT world. We've got new protocols like diagnostics over IP, for example. So all of these are going to have such an impact on how we test, when we test, how often we test, and how deep we go into the car. Machine intelligence, as I said, is a key enabler. And here, you don't have to read everything, and the slides will, of course, be made available afterwards. But I wanted to just say, in terms of testing and also in terms of the use of machine intelligence, we have been trying to use it as defense, but the criminals can obviously use it as offense as well. So where we look at multi-agent planning and cooperation, they are also able to look at multi-agent planning and cooperation. Where we want to ensure that path planning is safe, they can ensure that path planning is unsafe. So understanding the implications of how machine intelligence can be used as offense is also really important to test that, test whatever models, the data sets that come through, or whatever algorithms that are used or created. So those were things. Now we come on to data. And this is something I call a data jigsaw, if you recall, what do we know versus what we don't quite know. Well, one of the things that we do know about are the targets. So the targets are, at the moment, as far as we know, are the cars themselves. We also know some of the entry points, so we can test those entry points to make sure they're secure. We know some of the methods that are used, so we can simulate using those methods to see if the system is secure. And some of the attack patterns, because the beginning of every attacker is a human, they are able to make chained choices, which are these attack patterns. It's also important to understand, though, that it's really, it does have an impact on metrics, which I'll talk about in a bit. We also know who the attack actors might be, or are. So at the moment, very definitely, car thieves are definitely one of the attack actors. Maybe going forward, in terms of risk analysis and so forth, we would want to be considering whether terrorists would be part of this attack actors, whether it's someone who wants to blackmail somebody. I remember in America somewhere, there was a guy who disabled a whole fleet of cars because he was angry at his employer for firing him. So lots and lots of different motivations. And attack motivations. So we can run through some of the motivations for doing it. At the moment, car thieves are obviously doing it for money, but of course there are lots of other reasons that someone could attack a car as well. And we would need to, look at these motivations and actors and targets, we would need to tailor our testing patterns. One of the things we don't quite know yet is attacks in the wild, because currently cars don't have logging, or they do have logging capabilities, but the logging capabilities don't specifically look for security attacks. So that would mean that we would actually need a forensic system design, but we also don't know what that might look like, because forensic system designs, really at the moment, they're all very IT based. They don't look at how it would impact on a car. So if you wanted a forensic system, perhaps you need a unit that ends up in the car that specifically logs this kind of thing, but that unit could be more expensive, and it could be heavier and needs more wiring. And we know that cars that are heavier and need more wiring actually then impacts emissions, which there are very strict legislation for. So you can see there's a very finely tuned and balanced car. We also not quite sure about what the real world effects might be at scale. There's some simulation studies. For example, there's one that looked at whether vehicles, if you broke 5 vehicles down in the middle of Manhattan, what kind of traffic jam would that cause? There's that sort of simulation and testing going on, but we really don't know what the real world effects at scale might be. Probably catastrophic, but. So I mentioned earlier the ecosystem. We don't actually know where the system boundary should be for testing. As I said, should they be the car? Should they be the things connected to the car? Because the car can be used to attack something, and something can be used to attack the car. So of course we would need to consider all of those. But then if you imagine all the vehicle to anything connections that are being considered right now, we're talking vehicle to infrastructure, vehicle to building, vehicle to home, vehicle to pedestrian, vehicle to device, vehicle to grid even. That it starts to get bigger and bigger, and that's where there's a little we don't know where to stop it, or where the best place to place the boundaries are. We also have no metrics. Now, this goes back to attack motivations and attack actors. So although, for example, in a safety analysis, the laws of physics can be used. So, if you crashed against the wall with this material at this speed, what's the impact on the car in terms of crushing, for example, or in terms of deformation of the material? For cybersecurity attacks and risks, it's very difficult because so really need to think about the quality of the data that we use. And then correlation versus causation. So, I mean, this one not so much for automotive, but I have an example in terms of machine learning and data from a medical setting. So there was a study on whether patients with asthma suffered more with pneumonia or had worse prognosis with pneumonia than patients who did not have asthma. Now, common sense probably says that asthma, being a lung condition, would mean that you'd probably worse off prognostically with pneumonia. However, the study came back saying that asthma patients actually did have better outcomes than non-asthmatic patients. But what they didn't take into account was that human doctors had recognized that asthma would come out with a worse prognosis, and therefore paid more attention to them and intervened more, and therefore that's why we ended up with asthma patients having better prognosis. So we have to be aware of the correlation versus causation there. Now, in process, so things and data would need to, they'd be separate without a process. And so I spoke about security assurance earlier. Now, these are based on standards and best practice and lots of testing and analyses. It gives you confidence. However, it doesn't give you a guarantee. Now, confidence is really important. It's better than nothing, and it's current best practice, because we actually, don't have anything better at the moment. There's work being done towards it, but guarantees are very, very difficult in such complex systems. We've got governance, which can also help at an organizational level. So, legislation, monitoring, compliance, response, management, and deterrence. But one of the most important things in security and security testing actually is conflict resolution and how you would go about getting the requirements for these to resolve the conflicts and requirements. So, we've got a security versus safety conflict, for example. So, security best practice usually says if you've got a patch, test it as quickly as possible and then deploy it as quickly as possible. For safety reasons, if you did that and you get a blue screen of death halfway down the motorway at 70 miles an hour or 120 kilometers an hour, then we're going to be in trouble. We've also got security and privacy. So with security, you'd want to be monitoring everything as part of that practice. But if you're monitoring everything, then the privacy aspect of it becomes a bit less. Got security and usability as well. So it's well known in the IT world, for example, that the more security you put on something, and if you didn't give any thought about how usable it is, then people will find ways around it. Now, this is more so in a vehicle. So if you imagine a self-driving vehicle, it's got no driver in it, and all the people in there are your average person in the public. If they're asked to do something for a security reason, for example, if there's an attack, if you don't make it usable, how are they going to do it? And there may not even be an operator in the vehicle. And then, of course, the age-old security versus cost. Security costs extra, and that's one of the balancing acts there. Move on to people. Now, this is not yet in the automotive world, but is very much in the IT world, in that whatever we do is mirrored by criminals. So you've got crimeware as a service, you've got pay-per install, you've got crimeware toolkits, you've got brokerage, you've got data suppliers, and you can imagine, I mean, this is literally just a black mirror, if you will, to some of the activities that take place legitimately. And I wanted to bring attention to that number there. That number is the estimated profits made by cybercrime in 2018. A staggering number. I mean, if it was a country, it'd be 13th biggest in the world, more or less. So the point I wanted to make here is that this estimate is without some of the things that are happening in the automotive world. So things like, financial transaction systems that are being introduced right now to buy fuel, looking at or to buy charging, or looking at some of the safety issues that could be caused, around things like blackmail or ransom. We already know that the automotive industry, the manufacturing side rather than the automotive side, is being bombarded by ransomware. So none of that at the moment has made it into this figure, but you can see there the opportunity for a criminal is huge, which means that security and security testing is really important. There's also another aspect of people that I wanted to bring in that, in terms of design and testing, is this personal aspect where it's not illegal, but it just doesn't sit well with people. And this goes back to the trust bit. This is more human factors and how you might test for that. But, would you like your car to be able to detect if you're drunk? You've got enough what's the word for it? Individualism in how you drive your car that they can fingerprint. So that study there was done with 26 drivers, and within 8 minutes of the data coming through, and this is sensor data, not any other data. So we're talking, cornering speeds, acceleration, brakes, and how often and how hard you apply them. For the driver fingerprinting, within 8 minutes, they could tell that it was someone different, and within 2 days worth of driving data, they could identify who it was. So really, really important thing to look at there. This is a supermarket who figured out that a girl was pregnant and then sent her a leaflet before, and it wasn't her who opened it. Looking at some of the future technologies that we're looking at in terms of biometrics to open up the car, like your fingerprint or whatever it is. But here, for example, I wanted to say that if my credit card details were leaked, I'd probably just change credit cards, but it's really hard to change DNA. So some of the things that we want to think about there. So yeah, and I guess the last thing the last thing around people, at least, is the skills gap. There's a huge number of cybersecurity vacancies globally, and it's one of the fastest growing fields in terms of the automotive industry. But of course, having that skills shortage and that skills gap just means that criminals move even faster. They already move faster based on the spear and shield saying, in that criminals only need to find one thing, or just one thing to exploit, whereas defenders have to protect everything. So you can see there's a real problem there as well. So going back to the ecosystem is just like a screenshot to tell you, look how crowded the field is. Look at all the different kinds of players there are that really impact on testing. We've got infotainment applications, we've got autonomous driving, we've got fleet management, we've got insurance, we've got diagnostics, security, integrators, navigation, hardware, wireless networks. So big field. So that takes me to the Internet of Everything, basically. To summarize, in terms of things, especially from those of you in the IoT world, you know a lot of them are still largely unregulated, or the legislation is just emerging, which means that technologies and applications are. So that means that since they're just emerging, its application is still not quite certain, and its enforcement is still not quite certain. Technologies and applications are proliferating, converging, conflicting as well. So you can see that before, the automotive manufacturer, or whoever it was who put the car together, had complete control over their system. And if they were really, really good, they had complete control over their supply chain. But that's not the case anymore, because it would be a different supply chain that built the cellular mast that connects to your car. It would be a different supply chain that built the mobile phone that connects to your car. So that lack of control means the conflicts and the convergence is largely unmonitored. And of course, we have legacy systems and requirements. Now, I mentioned vehicles, from design right to the end of its lifetime, we're talking 20 odd years. For infrastructure that's connected to it, we're talking 50 years. For ships, we're talking 50 years. We're talking, decades in such a fast moving field. And this has very much a thing to consider. And I mean, we can see that already. I don't know if any of you heard, but NASA was looking for Fortran and or COBOL programmers to work on its space probes, and that would be part of the consideration that we would have to take into account as well in terms of testing. Data. So we've got still missing some pieces. beware of garbage, correlation, not causation. And I guess the point, the summary that I wanted to make here is that prediction in terms of risks and threats and so forth, it may not be measurable by a single variable, but since we're missing so many pieces, it's really hard to say, and it's still something that we're working on. The process, so things and data would be disconnected without a process, but they need to cover many aspects. And one of the most important things, I guess, for security and security testing is that it's an overall system property, and it's more than the sum of its parts. So it'd be, and also looking for emergent behavior, especially in dynamic systems like AI, where it constantly learns and makes decisions on the fly. We would need that kind of traceability through it as well. And then people, so considering multiple angles of people, who takes advantage, who would benefit, who do we need, what kind of skills would we need? Obviously really important for carrying out that sort of testing. I also wanted to introduce one of our offerings, which is vehicle resilience, which brings together all of these disciplines and all of these thoughts and all of these practices together in the best way we know how in terms of looking at vehicles and also autonomous vehicles. So that's pretty much me. Thank you very much for listening.
Hi, Madeline. Thanks. Great talk. I have an echo. There's some questions already on Slido. If I can remind everyone to go on Slido, Tesena Fest is the code, put your questions there. So the first question is from Pepper, who wants to know, how does he start testing these things? He wants to start testing these things. What's the best place to start in terms of resources, books, blogs, YouTube videos, or whatever? What could you recommend to him?
So sometimes people think cybersecurity is, so probably the best place to start would be to look at a concept called cyber-physical systems, because that's what these cars are. They were completely physical before, and now they've got software elements attached to it and their networks. Now they're cyber-physical systems, and they're different from pure cyber systems in that the impact isn't just data being lost or data being destroyed or data being manipulated. The impact actually is physical. So, if you hack a robotic arm, the safety impact is physical. Because why I say that is because when you start looking at testing it, depending on where you want to specialize in, you could look straight from the electronics level. So we're looking at circuit boards and how they work and how you could introduce defenses to that, right through to the really high level sort of looking at training data sets for AI, that sort of thing, or even higher still into the cloud, for example. It depends on what your interests are. There are actually many layers to it.
Okay, thank you. I have a question myself. For the advantage of being moderators, I get to ask questions. So I liked in your presentation that you didn't take just into account the hacking, the stealing, the getting your data, getting your property, but the use cases, the people use cases. For example, I remember a few years ago renting a car and finding that the guy, previous renter, had left his home address in the navigation system. And I think these are some of the things that we as testers, we can think about, even without knowing any of the security testing issues.
Absolutely.
What's your feeling about that?
Absolutely. I mean, there's been some recent cases where obviously you can register to connect your account with a dealer, for example. In fact, you can connect through this app to start the engine and unlock the doors. And there's been a couple of incidences in the press where the car had been sold to a new owner, and the old owner still had access to unlock the doors and start the car. New owner, and the old owner still had access to unlock the doors and start the car engine and track the new owner. So the sort of how the intersection between the manufacturer's design testing of that versus the and also the dealership as well, and how the dealership might deal with it. Absolutely, the use cases there would need to be considered. And I guess what's interesting is just how many different use cases there are now, that the car is so much more complex.
Okay, so I've got another question from Andre. He's asking if to summarize what's in terms of your testing experience, what's the most problematic test cases you have to design from an overall complexity point of view? What are the things which are most difficult to try and test?
The most difficult thing is to try and test, I think, is actually the vehicle itself. And I think I mentioned before, it's literally because there are layers of it. So, you've got your electronic security, you've got your sort of, very low level firmware based security, and then you've got your high level, and then your software, and then your network, and then your cloud connection to the car, for example. That's one of the things that are really hard. And then what makes it even harder is the system boundary is really fuzzy. Don't quite know what the best system boundary might be. It might depend on each vehicle, it might depend on each manufacturer. And the last thing that makes that car just so difficult is the supply chain, or the way the supply chain is set up. So if you imagine there'll be someone somewhere down the supply chain, downstream of the supply chain, selling chips. Of course, they will give you enough to tell you enough information to tell you how it works, but they will never give you the design, will they? They'll never give you the fab or where they fabbed it or anything like that. So now you've lost a little piece of testing information. Then the chip is then put onto a printed circuit board, and even though the printed circuit board, you can test your...
From Martin, thanks everyone for the questions. Do you implement tests during the implementation, or you have testing team stages separated from the development? So it's more if you're testing close to the development, or you're testing after the development?
Well, we offer testing as a service, so it depends on what the customer wants. It's been anywhere from component level right up to, because we have a proving ground that's basically for connected vehicles, and we're building another proving ground for connected autonomous vehicles. Assured CAV Highway is called. If you're interested, it's an investment worth over £30 million. So that one's for automated vehicles. It's at every level, depending what the customer wants.
Okay, and question, we're almost out of time. Another question from Andre, who says, thanks for an excellent talk. So how big is your testing team? How many people do you have?
We have an entire segment of the company around testing. It depends on what kind of testing. So we've got electrical testing, with all the new batteries, for example. We've got proving ground testing. We've got EMC, electromagnetic compatibility testing, because obviously all those electrical equipments give off electromagnetic radiation, and sometimes it might not be safe. So we've got that kind of testing. We've got climate testing. We've got software testing, hardware testing, all kinds. We have an entire company segment based on testing.
Sounds fantastic. Sounds like the ideal world for me.
Absolutely.
Okay. Madeline, thank you very much for your excellent talk.